our team code kottu, and this is our approach to the problem statement.
Okay, so when we start off with getting the request from the system, what we do is we first try to predict the type of file that has been sent using the URL. So according to the type of file, we are going to use different methods for extracting the text. And if it's an invalid type, like for example zip file, we are going to say we are not able to process it. And at the same time, how do we? So when the document comes to the URL, we download it and then extract the text from it. And it is not only happening in a simple manner, but also in a manner such that if there are tables in it, it is taken care of in a structured way. So after we get the text is extracted, we're also checking if there are any URLs inside the text, which we are using for complicated questions, which we'll get to later. And after we get all of the text, we have to think, why cut a cake with a chainsaw when you have a knife? That's where we are using simple text questions process, where we are sending all of the context through a single API call with all of the questions to get the answers. And this is being done only when the number of characters extracted is less than 7,000 characters. So for less context, we're sending all of it at a time to ensure efficiency. Now, coming to the chainsaw, the RAG, the main system of our project. We are using an assemble retriever, which is having which is a hybrid system. It has BM25 and it has FISS. So we are using both semantic and keyword matching here. So what we're doing is we're doing 0.4% weightage for BM25, and at the same time we're doing 0.6% for FISS, which is the recommended ratio. So what we're doing is we are getting the context, we are chunking it, we are vectorizing it, and then doing it according to the BM25 ratio. We're getting the top 3 chunks, top K chunks, which is 3 here, K value, and then to ensure that there is efficiency in the system that we have built, to ensure there is high accuracy, we have made a system which is HYD, which is hypothetical document embeddings. So rather than just going and trying to retrieve, we are first generating a hypothetical answer and then vectorizing it so that we have the relevant chunk of text which is relevant to it. We get the relevant vectors. And similarly, we are also decomposing the question into simple parts. So if the question is complicated, we are making it simpler. So it's not just isopropyl alcohol, but we're using heat too. We're cleaning up the question. Along with it, we're decomposing it with heat. So let's see how it works. So first, we send the chunks for the questions. We ask to generate simple questions, decomposed questions, and along with that, the hypothesis answer for the given question. And then we vectorize all of it, and we get relevant chunks according to the questions and the hypothesis generated. So let's say there's a very long question with multiple questions, so we get a lot of chunks accordingly. So according to the number of questions asked, we get those number of chunks, and hence increased accuracy. So for final, so from this, we are going to send all of the chunks into our final generate final answer function, where the chunks are sent, and we have our prompt to answer in a grounded manner for the question along with the context. And then we have the assemble answer. So when all the sub questions are created, each of them are answered using this function, and then all of them are assembled together, each of the questions. So all the sub questions assembled into a single answer using the assemble answers function. And we have the biggest orchestrator of our RAG system so far, which is answer questions in parallel to ensure that we get the answers in as fast as possible. So what we're doing is we're sending generating answers for each of the simple questions in parallel, and then all of them are being combined in parallel too, so that we get the answers to the questions in the quickest way and the most accurate way.
In case of a website URL sent as a request or a PDF with multiple URLs, we follow this approach. We first smartly detect if if the URL sent is an actual API endpoint or a normal document file. If it is an API endpoint, then it returns the data. If else, we process the document file normally. We detect if the PDF requires web scraping using strong indicators, moderate indicators, and negative indicators. We calculate a score with the help of these indicators, which helps us to tell if web scraping is necessary or not for only the document part. We then analyze different PDF content types such as travel, form submission, or documentation, etc. We extract URLs from the text using validators in the regex pattern. Then we scrape URL context. Then we scrape the URL for context. We use a beautiful soup library to do this. We scrape all the data from the website. Then we process PDF with the web scraping. This means we send the PDF content along with the web content, that is the website content, to the LLM to generate proper answers with proper output formatting.
Intelligent caching, verification and refresh. Dynamic web pages can change over time. So our process allows rechecking. First, we save a clean version of each page's text along with a unique fingerprint. Later, we revisit those pages and compare new fingerprints to the old ones. If they match, we know that the content hasn't been changed. So we reuse the existing answers. If they're different, the content has been updated. So we fetch the latest version, merge it with the original document, and regenerate answers to keep them accurate.
The image and PPT processing workflow. So for efficiently handling images and PowerPoint slides, we use Google Cloud Vision API. So for optical character recognition, in short OCR. So this allows us to extract text from visual content with high accuracy. So as you can see, there is this function. First, we will get the Google Vision API key from the environment variables, and then we'll create a API client. So after that, once the text is extracted, we send to the Gemini API, which processes content and generate answers to user queries. So in this way, we can extract the text inside an image and generate answers to the user queries. So coming to the PPT section, so the PPT function. So processing multiple slides or images can be time consuming. So to accelerate this workflow, parallel processing comes into play, or asynchronous processing. Okay, during the OCR phase. So it extracts text from multiple images simultaneously. So this minimizes the latency in overall pipeline to deliver results and more efficiently. Yeah, faster and more efficiently.
Right now, our model can cache intelligently by examining whether the context is dynamic or static. Intelligent model selection uses a blend of 1.5 flash and 2.5 flash according to the complexity of tasks. It also selects a method whether simple or RAG-based answering. Also, intelligent tool selection whether to scrape the URL or not. This type of system is often called as reasoning and acting agent, which is React. But we want to go further and make it fully agentic, and this is our future plan. Thank you.